Hello guys, welcome to Civil Softwares. Today we are going to solve one complete numerical of direct stiffness method of a simple bar element. But before that, I want to explain a little bit of the background which will be used in solving those numericals. Okay, how to find the stiffness matrix? Because stiffness matrix is the vital thing that you need to find for solving any finite element problems, because as we know that we have one formula F equals to Ku, and this guy here is the stiffness matrix which we need to find. So let's say case 1, which is rather very simple. um, so for example, if we have this bar, which is a simple bar, and we have two nodes here, and the dimensions or the characteristics are it has the area of A, elasticity E, and then the length is L. Okay, so what else do we have here? Just to distinguish this, so we have the external applied force F1 dash. Okay, here F2 dash, because this is node 1, this is node 2, and I'm putting dash here because we are dealing with the local system, which is actually same as global system here, because normally what we say is in our global system we have the x-axis and y-axis perpendicular to each other like this, and the bar here is exactly parallel to the global x-axis. That's why we call this as to be in local system, and for local system we put dash. Okay, for this case this is the local system as well as the global system because it aligns perfectly with the global system. In another case you will find the major difference between local coordinate system and global coordinate system. So you have f1 dash there, and let's say you have displacement of u1 dash over here, and here u2 dash. Okay, so now if you have to find, if you have to use this formula over here, let's say this is equation 1, then what would you do is you would say, okay, f1 dash, f2 dash, just collecting the forces for both the nodes, equals to, we will have some stiffness matrix here, and we multiply that with the respective displacement u1 dash and u2 dash, right? So we need to find this, and I have uploaded complete derivation for this case in my first video of finite element methods, but here I'm just going to roughly give you the idea. So for finding the stiffness matrix here, K, we just use this formula, which is A E upon L. Okay, AE by L, but while using this stiffness matrix formula for equation number 2, we have to multiply with uh, another matrix, which is f1 dash f2 dash equals to, as I said, stiffness matrix K comes out to be AE upon L, and then 1 minus 1 minus 1 1, and then You just do u1 dash u2 dash. So now this becomes our stiffness matrix K. Let's say this is equation number 3. Okay, so you use this formula to find the stiffness matrix for a simple bar element which is aligned perfectly with the global coordinate system. So let's look now at second case. So our element will always not align with the global coordinate system. Let's say we have this global coordinate system. Okay, so let's say this is global X, this is global Y axis, and then we have one bar element uh, like this one here. Okay, okay, so we have a bar element like this, and as you can clearly see that there are two nodes. Let's say this is node 1. Okay, this is node 1 and this is node 2. I didn't write it because there are lots of things to write here. It would be a mess. And okay, so this is our global system, X and Y, but our element is not aligned perfectly to the global coordinate system. So this element will have its own coordinate system, which is our local coordinate. That's what I was talking about in earlier videos. Now this element is aligned something in this direction. Okay, so this will have its own local coordinate system x dash along this direction, and perpendicular to this, like this direction, perpendicular to x dash, you will have y dash, which is its local coordinate system. Okay, so it's simple now, and we just let's just use the black marker. So let's say, let's first deal with the global coordinate system. Okay. Okay. Uh, so let's say in global coordinate, you have in this direction force 1 along x direction, and I'm not going to put dash over here because it is global coordinate system. And along this direction, you have displacement u1x, right? Similarly, you will have the same kind of things in y direction as well. So this is f1y, and you will have u1y. Okay, and for node 2 along the global direction, you will have f2 along x, u2x, and then along y you will have f2 of y and u2y. So we did not use any dashes here because it's global. Now let's say we deal with the local coordinate system now, because actually the forces applies in the local direction. So let's say in local direction, when we convert, we have this direction instead of this. Okay, it is just a conversion. Okay, so and along y direction you will have in this direction. Similarly for this, as I already drew it, like along x dash and along y dash. Okay, so now since this is in local coordinate, we write f1 x, but we use dash over here, and u1x, but it's in a local coordinate system. Similarly, for this case, you have f1y dash and u1y dash. Yeah, I hope you understand this. Along the second node, you will have f2, oh sorry, f2x local, u2x local. Along y, you will have f2y local, u2y local. And by the way, the area is A for this, and elasticity is E. Length along this direction obviously is L. So in this case, now you will have a transformation matrix, which is very important. Transformation matrix. And what does this transformation matrix do? A transformation matrix, we call it T, okay? And what is its job? To relate local and global system, okay? To relate local and global coordinate system, we have this relationship. So for example, you have to relate local displacement matrix U dash to global displacement matrix, then you would have to use this transformation matrix to convert the global coordinate system into local. So this is our local coordinate system. This is our transformation matrix. Okay, this is our transformation matrix, and this is in our global system. Okay, then what is this transformation matrix then? How to find it? Simply, let's say this element is making, let's say this is the center of this bar, and it is making, I will use a distinct color for this one. Let's use this one, okay? Let's say this bar is making an angle in a anti-clockwise direction with global x-axis, and the angle is theta. Okay, it's theta. Then you would simply do this way. Transformation matrix T would be C S minus S C. C S minus S C. Rest of the terms 0, 0, 0, 0, 0, 0, 0, 0. So this is your transformation matrix, which you can use to convert the global coordinate system to local coordinate system, where C is cos theta and S is sin theta. Okay. You will see its use in a practical numerical. So now this transformation matrix is used to find the stiffness matrix for this kind of slanted bar. So for slanted case, if we have to find the stiffness matrix, then we just use this formula. So this is the stiffness matrix global, okay? And then you just use the transformation matrix, its transpose, okay, and then Ke, which is elemental stiffness in local coordinate. Ae by L, 1 minus 1 minus 1, 0, the thing that we did earlier. And then again the transformation matrix. Okay. Okay. Uh, Here, okay, for local stiffness, Ke dash, if it is two-dimensional, then we simply do Ae upon L 1 0 minus 1 0, okay, and then 0 0 0 0 minus 1 0 0 sorry, minus 1 0 1 0 and then 0 0 0 0. So in previous example here, when we found out, when we dealt with this thing, we did only one dimensional, didn't have the y coordinate, that's why we didn't have this big matrix. But now here we have x-axis as well as y-axis, so we have to incorporate those as well. Okay, so this is the local stiffness. And when you solve for the transformation matrix, which is this matrix here, and multiply these stuffs, then you are going to be left out with one simple formula which you can directly use. You will get a stiffness matrix for the slanted would be Ae upon L, and simply so there is one like various tricks to remember this. I like to do it like this. So c square s squared, and again c square s squared. So I would first finish these diagonal terms, okay, and then you just move cs. Once you do this, you just change the sign. So it's c square here, then here it will be minus c square, here it will be minus cs, okay. For example, here is cs, and it works in all directions, okay. So for example, here is cs, here is s square, okay, then here it would be minus cs minus s square, okay. See, here it's c square here, then here it would be minus c square. It's very simple actually. And then since here is minus cs, here it would be positive cs. And since here is s square is positive, here it would be negative. So in one direction it's positive, and in another direction it's simply negative. So c square cs, similarly here c square cs minus c square minus cs, okay. So minus c square, then minus cs, because here is positive cs, here would be minus, and then here would be positive. So you use this formula whenever you find that the element is slanted. Then you can directly find the stiffness matrix and move forward. We will see this implemented in our next practical example. So here we have a simple bar element where we are going to use direct stiffness method to find, first of all, stiffness matrix, then displacements at nodes 2 and 3, and then reactions at node 1 and 4, and element forces. So there are three kinds of elements here. One in the green has 200 Newton per mm, second element has 400 Newton per mm, and third element has 600 Newton per mm as their stiffness value. And we have four nodes. So let's start our task. Number one. Okay. At first, let's just in step one, just simplify the model, discretization. Let's do the discretization step. Okay, so in discretization step, we simply simplify this figure like this. Okay, it's straight, completely straight, but I'm just drawing it roughly. So this is node 1, this is node 2, this is node 3, and this is node 4. Stiffness values are already provided, so I will just write here K1, K2, and K3. And this is element 1, this is element 2, and this is element 3. Okay. And now let's just provide another color for this. Okay, so displacement for this element, let's say it's u1. For this second node, sorry, not element, node is u2, and this one is u3. We only have horizontal displacement here. This is u4. All right, and this is our global x-axis. Now let's collect what we have in step number 2. Okay, let's just collect the force vector. The force vector F, force vector F is just the collection of all the forces which is available here. So for the first node, we can see the force is the reaction from this fixed support. Just keep R1. For this second node here, we can see there is no external load application, so it's 0. For the third node, there is external application of load 25 kilonewton. So you just put here 25. And then for the last node, similarly, it's the reaction. Okay. So similarly, we have the displacement vector as well. Let me just shift this. Okay. So we have displacement vector, which we denote with u. And since this is just the local coordinate and the global coordinate is basically the same because it's along the x global, let's just say this is also local and this is also local, which is same actually, and it does not matter in this condition. So for the first node, it's u1, second is u2, third is u3, fourth is u4. Okay, so this is done. Now similarly, we have our boundary conditions as well. So what are the boundary conditions? Okay, now I will just collect the boundary conditions here. So boundary condition is basically what you know, okay, what is given to you or what you know from the figure. For example, if you see in this example, u1, here this u1 is, here we have the fixed support, so this node is moving nowhere, so u1 will be 0 here. Okay, similarly for the fourth node also there is fixed support, so u4 would also be 0. So using the boundary condition, we just have our displacement vector as like this. u1 is 0, u2, u3 we have to find, and u4 is also 0. Okay. Okay, so now let's go in the third step, which is to find the stiffness matrix, which is our task A. Okay, task A is finding stiffness matrix. Mhm. Okay. Stiffness matrix. So we have to find the stiffness matrix for the element 1, element 2, element 1, element 2, and element 3. Okay, so let's go there. So you basically use a same simple formula for everything. uh, okay, so you have this formula for finding the stiffness matrix is K equals to A E upon L, right? And 1 minus 1 minus 1 1. Okay, but we already know the value of A by L for all the elements, right? So for element 1, um, I've given which green color? Okay, it's 200. So for element 1, let's go for element 1. For element 1, we have been given A E upon L, which is the stiffness value, as 200 Newton per mm, right? So we just say K equals to, this is for element 1, so let's just write 1. So value of A by L is 200, and then we have 1 minus 1 minus 1 and 1, right? And this is it. Okay, let's say this is equation number 1. Okay, so for element number 2, so for element 2 we have provided the red color here. This is for this red element 400. Okay, similarly for element 2, for element 2 we have been given the value of A upon L as 400 Newton per mm twice. Okay, so K2 would be 400, same formula, A by L, 1 minus 1 minus 1 1. So this basically gives us equation number 2. Okay, just keep it this way, or we can also actually do like this. Wait a minute. So we can actually simplify this by taking the 200 common. So 2 minus 2 minus 2 and 2. So this will be better when we assemble all the elements at last. For element 3 now, we have given green color, I guess. No, green, sorry, it's blue. So it's 600 Newton per mm. 600 Newton per mm. Okay, so it's 600. Okay, and now for element 3 we have been given value of AE upon L as 600, I think. Yes. Okay, so it's 600 Newton per mm. Then we will have our K3 as 600 times 1 minus 1 minus 1 1. Since we are taking 200 outside, so that we can take common from all, so let's take 200. 200 times 3 is 600, so 3 minus 3 minus 3 and 3. So this will be our equation third. Okay, okay, now we just need to assemble this. I will just zoom out a little bit. Okay, So if you see mm, um, in this figure, there are some common displacements. For example, if we look at this element number one, then the displacement at U2 is concerned with this element as well as this element. And similarly, the displacement for node 3 is not only because of the element 2, it's also because of the element 3 because they are connected to each other, right? So while assembling them, we need to add the collective effect of all the elements, okay, of all the displacement elements. So for example, in element number one, let's do it with very basic. For element one, we can just say that this value, which is 201 minus 1 minus 1 1, is concerned with displacement at u1, displacement at u2, displacement at u1, displacement at u2. This is this common idea, which will be very much useful. I will show you. And similarly for element 2, when we say it's 200 times 2 minus 2 minus 2 and 2, then it this second element has u2 and u3, right? So u2 and u3, u2 and u3. I'm just giving this indications. It is nothing else. And for element number 3, I'm going very basic. You might be bored as well, but anyways, so 200, 3 minus 3 minus 3 and 3. So element number 3 is concerned with displacement 3, displacement 4, displacement 3, displacement 4, right? So now our job is to assemble all of these. Okay, now I will just be a little bit like this one, and I will write here. Okay, I'll write here now. So now our idea is to assemble all these, assemble the stiffness matrix. Okay, so now we have to assemble the stiffness matrix, and once again I will quickly draw this indicative figure only. Okay, this is 1 2 3 4, and this is element number 1, this is element 2, this is element 3, and this is u1, this is u2, this is u3, this is u4, and here u1 is 0 because it is fixed, and u4 is 0, and sorry, this is u2, this is u2, and okay, we need to find u2 and u3. Now let's make this global stiffness matrix. So K. Now I would also like to tell you that the order of the matrix would be equal to the degree of freedoms. Okay, very good. So the basic idea would be to just draw this one, and then we know. Okay, I will choose yellow color. Okay, for this one. Okay, so just for indication, so we have displacement u1, we have displacement u2, we have displacement u3, and we have displacement u4. Similarly, I would just draw here as well u1, then u2, then u3, then u4. This is going to make your life very easy. I have this experience in exam. So just be systematic, and though it looks a little bit easy, in exam you have to be very fast to do these things. So just get basic idea about this. Okay, I'm just going to draw this. Okay, we have this place for all of them. Oh, this one. And we have for u1, u2, u3, and u4. Okay, so when you look at the stiffness matrix for the first element, this one, then you see you are concerned with u1 and u2, and here also u1 and then u2. Now basically you are just concerned with which boxes, u1 u2 and u1 u2, intersection between. So first of all, look at this row and select which components are you interested in. You are interested in u1 u2, and similarly for the column also you are concerned with this column, column and this column, right? So intersection between these two leaves you with the space, this. Okay, so this is the space which is occupied by the first element. Okay, so I'll just uh, write this in green because I wrote for the first element as green. Okay, so now since we took 200, 200 is common in all of this, so we can take that 200 out actually. So just remember, okay, let's just quickly do it so that we do not get confused. Since 200 is common in all of these, you just make this 200 outside. Okay, so just 200 times whatever comes here. Yeah. Now for the first element we have 1 minus 1 and then minus 1 and then 1. So our first element is done. So now second element, I will use the red color. So second element is this one, 2 3 and 2 3. So first of all select, okay, you are concerned with this and this, and here you are concerned with u2 and u3. So intersection between those gives you the space, this one, this one, this one, and that one. So we are going to fill up this, and if there is already another number, we are just going to add. Okay, so just remove this so that I can write. So our first element is 2, which I have to add here. Second element is minus 2, which is alone, no need to add anything, and minus 2 and 2. So our second element is also done. So we go to the third element. So for the third element, you can see for the third element, we have u3, u4, u3, u4. So our point of interest is u3, u4 and u3, u4. The intersection between those leaves us with this space, this one, this one, this one, and this one. Okay, so we just fill up these spaces as they are in their order, like 3 comes here, plus 3, here, minus 3, here, minus 3, and here, 3. Okay, since now let's finalize these answers. So 2 plus 1 gives us 3. Here it will be 5. Yeah. So this leaves us with this answer. So if we collect this nicely, what will our stiffness matrix be? Okay, let's see. So stiffness matrix would be 200 times 1 minus, and other spaces will be left with zeros. Okay, 0 0 minus 1, 3 minus 2, 0 0 minus 2, 5 minus 3, 0 0 minus 3, and 3. Okay, so this is our global stiffness matrix. Okay, now finally we solve these equations. Okay, now we know that we have to use force F equals to KU, right? So we already have the force vector from previous writings. So first one was reaction one, and then there was nothing, and then there was 25 kilonewton of load. Then there was reaction from another fixed support R4, and K would simply be our stiffness matrix, which let's see if I can copy this. No. Okay, I'll just copy this and paste here. So, okay, nice. So this one is our stiffness, and then we also did the displacement vector as 0, u2 and u3, which we had to find, and u4 is 0 because there was fixed support and the node is going nowhere. So now we just need to find the answers to this. Okay, so the basic idea is to uh, solve those values which we already know. For example, here we know it's 0 and 25, right? We know these values. So we can get two equations and we have two unknowns and we can solve this. So basic idea is now you just remove the unknowns. So remove the unknown force sections, meaning both rows and columns. Here, what does it mean? So remove the so this means that you just remove the rows and columns concerned with R1 and R4 because you do not know it. Okay, so just remove this whole row. If you remove this first row, you will have to remove the first column as well. Whatever row you cancel, you have to cancel that column as well. So in reaction 4, also cancel this one. Okay, and reacts if you cancel fourth row, fourth column should also be cancelled, and then you are left out with this inner section here. Okay, and then this is going to be solved and you are going to get nice results. Now, okay, now we are left out with 0, 25, okay, because we cancelled R1 and R4. This is 200, which is common, so that it does not get cancelled totally. So 3 minus 2, and 5 are remaining. And then we have u2 and u3. Okay, so this is what we are now left with. Okay, now if you do okay u2 u3, if you bring this on the left hand side, and if you bring all of these in here, then you are left out with u2 and u3 only. So 200 goes down. Okay, then you will have the inverse matrix of 3 minus 2 minus 2 5. Then you'll have to inverse this matrix and then multiply with 0 and 25. Okay, this is very easy to solve with calculator. Once after solving, what you get is after solving um, mm, use calculator, of course. Just write it, use calculator, then you will get u2 as 0.0 227 mm and U3 0.0340 mm. Okay, so you got these values now. So using this, now you can finally find the reaction forces, um, which we canceled here. Okay, so let's just do it. Solving for forces now. Okay, so F1 was our reaction 1, and then we had 0 because we had no force and it's 25 kilonewton, and then we had R4. And then I will just copy paste. Okay, this thing, this is stiffness. Okay, okay, and then the displacement values which you found already. First displacement was 0, second displacement is positive 0.0227, and third we got 0.0340, and the fourth displacement was 0, of course. And note that, for example, we got positive value here, which means the direction for displacement that we chose was correct. If it had come negative, then our direction would reverse. We did U2 in this direction. If it came out negative, we would have the displacement in opposite direction to what we thought. Okay, just telling. And now you get these values and you can solve this very easily using calculator as well. So after solving you get uh, R1 values, sorry, R1 value as minus 4.54 Newton. So exactly what I was telling, opposite to our direction. Okay, opposite to our direction. That means we said that, okay, this was our fixed support, and we said, okay, reaction 1 would be like this. But no, it turned out to be negative. That means our reaction force would go this way. Okay, so this is right now. And then reaction, sorry, not 2, it's 4, the last one is minus 20.4 Newton. That also means that for this, which direction did we choose? We chose, I think, this direction, but it turned out no. The correct direction is this one. Okay, so if you look at this figure where we did this one, okay, so yeah, we we said, okay, reaction flow is in this direction, but it was wrong. It turned out to be in exactly opposite direction. Okay. Mhm. Okay, so we solved for the reactions as well. I'll just highlight this one. So we got our reaction values, and we also got our displacement values. Now our task is like forces in each spring. So forces in each element, let's say each element is what we found out the reaction forces, but now we have to find the forces in each spring. So now what we are left with is we had, okay, we had this here, and okay, something like this, and we found out that reaction 1 was in this direction. It was opposite to what we thought, 4.54 Newton. Okay, and reaction at 4 was minus 20.4, meaning this would go in this direction, 20.4, Newton. Okay. And here it was this way 25 kilonewton, right? Mhm. And this is element 1, so this is element 2, and this is element 3. And now our task is not to find the nodal forces. Our task is to find the forces which is experienced by these individual elements. What is the force experienced by the first element? What is the force experienced by second? And what is the force experienced by the third one, right? So for that, what we do is, so for element 1, for element 1, for element 1, what we do is F1 in x direction and F2 in x direction, right? Which basically means force in this direction for F1x, force in this direction for F2x. Let's see, this is force in third and F3x, and this is 4x, okay? This is what we are finding. This one is equals to force equals to Ku. It's the basic formula, F equals to Ku. And okay, I will write it one more time, F equals to Ku. And then for the first element, what is our value for, I will just write it one more time, A by L, and we go 1, minus 1, minus 1, 1, and then we have our displacement at U node 1, U node 2, because this is the section we are concerned about now, okay? And the value of this A by L is the stiffness that we are given, which is 200, okay? And 1 minus 1 minus 1 and 1, and then the first displacement is 0 because it was fixed support here, and the second is U2, which we found out to be 0.0227 mm, right? Yes. So after solving this, what you get is minus 4.54 Newton and plus 4.54 Newton. This is F1x, this is F2x, okay? So if you got the piece for the element 1, it will be something like this, and F1x would be like this 4.54 Newton, and this is positive, meaning this direction is correct, okay? This is plus 4.54 Newton, which means it is tensile force because it's pulling each other apart, so it's tensile, okay? And again, let's go for element number 2. Okay, so for element 2, similarly we do. For element 2, we have F2x and F3x, right? Okay, F2x and F3x. So similarly, A by L, and it's 200 times, what was the value? It was 2 minus 2 minus 2 and 2. Yeah, yeah, we did this because we have been given for element 2 the value of AE upon L was 400, so we just took common and multiply the inner terms, okay? So this is K, and then the displacement we are concerned with U2x and U3x, right? So what we get is 200 times 2 minus 2 minus 2. So u2x, what was the value of u2x that we found out? It was 0.0227, and u3x was 0.0340. After solving, you get f2x and f3x to be minus 4.52 Newton and plus 4.52 Newton. Okay, this is f2x and f3x. If I just zoom out a little bit, then we again got this figure. If we see this only, then we see, okay, this is element 2, then this minus 4.52 means it's going this way, and this one is going that way because it's positive and it's fine. Okay, so now let's go for element number 3. Okay, so for element 3, we had been given A by L value as 600 Newton per mm. So we just take common and multiply with 3 inside. So we are left with for element 3 we have f3x and f4x equals to 200 times 3 minus 3 minus 3 and 3 because we took common, and then the displacement at, okay, once I will write it, u3x and u4x. u3x value, what is the value of u3x? We found out 0.0340, and u4x is 0 because it is fixed support. So after solving, you get f3x and f4x as plus 20.4 Newton and then minus 20.4 Newton. See here, this is also in tension, element 2. And now if we see for element number 3 and our last element, we see that f3x is okay, positive. That means our direction is correct. And for f4 we said this direction, but it was wrong, so it's 20.4 Newton in this direction, so it's towards each other, so it's compression. Okay, so this is a compressive force.